Hi everyone, my name is Jane. Welcome to the Build Squad stage. We're going to be here for the next few hours hearing very interesting speakers. The first person up, his name is Ben Greenberg. He's a DevRel, and he's also writing a book on this very interesting topic, a vector search for decentralized systems. Come up here, Ben. Ooh. I'm going to throw the mic to you.
Thank you, thank you. Good morning, everyone. If we can get the presentation on there, it would be amazing. Yay, hello. Good morning, good morning. It's really great to be here to talk about, I think, a really important topic, which is vector search, and how to bring it into our applications and our utilities in our decentralized space. First, before we begin, my name is Ben, and you can find me basically at all places at hummusonrails.com. I happen to like hummus quite a lot, and I'm an old-time Ruby on Rails developer, so hummusonrails.com, you can find me basically on all socials. Love to talk about this topic with you later for the rest of the day or online at some point. Please reach out and say hi. So let's set our conversation with the right sort of frame of mind. And to do so, we need to really set our expectations, which is at the end of the day, data is basically garbage. Now, that may sound a little weird to you. Data is basically garbage. But what I mean by that is, you collect your trash over the weeks and months, and it gets your house smelly and stinky, and it's useless, got no utility, until you start processing it, sorting it, and making it into something that can be used as raw materials for new things. In the same way, data, when it's just a massive heap of stuff that you keep on adding to, all it's doing is adding to your storage capacity. It's not actually doing anything for you until you analyze it, process it, and sort it. And that's exactly where vector search comes into play. So we're going to cover a couple things in our short time together. We're going to talk about what exactly is vector search, a brief introduction. We're going to look at a decentralized paradigm for training AI models to help us with it, some use cases in Web3, and then a big question, which is what to do with all of the off-chain data that we need for our applications and utilities as well. So let's just get right into it. Vector search, for those who are not familiar, is the idea of taking your data, whether it's text, audio, video, doesn't really matter what it is, and turning it into representations of that data, what's called a vector embedding, to search for it through semantic retrieval, which is a fancy way of saying searching for it with natural language, using human words to find things. Now, not just keyword search, but actually conceptual search, relational entity search, conceptual search, being able to retrieve back items that are not just keyword matches to what you're searching for. And this creates a much more intuitive, much more natural user experience in our applications, in the things that we are building. That's essentially what it is in a nutshell. It takes your data, whatever your data is, DAO proposals, NFT metadata, transaction histories, and converts that into what's called those vector embeddings. And those vector embeddings help create accurate search, content recommendations, fraud detection. That's actually right, fraud detection. We're going to talk about that also in just a few moments, and a whole lot more. Now, what exactly is a vector embedding? A vector embedding is really nothing more than an array. It's a list. It's a list of numbers, specifically floats, meaning it's got a decimal in the middle there, and negative and positive integers. That is all a vector embedding is. Now, there's thousands of numbers for every piece of data. Some of our embedding models create thousands of numbers representing each piece of the data. So they're very big. But those in vector embeddings, each number represents a piece of information about that data. But how are those vector embeddings made? How do you go from DAO proposals over here with text into a bunch of numbers over here? How is that possible? Well, that work, it's not magic. It's actually not magic at all. It's just pure data science. It goes to an embedding model. An embedding model is a subset of AI models, right? So now we talk about AI, you gotta talk about AI all the time, right? It's a subset of AI models that takes text or images or audio, data of some sort, and analyzes it and produces the embeddings. Embedding models basically work like your brain works. You are watching me talk right now about this, and you may remember a conversation you had yesterday, or something you read a few weeks ago. You are mapping the data in your brain, which is very similar to what an embedding model does, maps the data to each other. It's sort of like a neural network, which is really, really cool. And the way that that basically works, taking one example, you may have heard of these three letters, GPT. You may have used ChatGPT this morning at some point before you got out of bed, I don't know. The way this basically works is you feed the data into the embedding model. Let's say you're using an embedding model from the GPT class, a generative pre-trained transformer. The data you pass through to it gets chunked up into smaller pieces called tokens. Those tokens are sent through layers of understanding. Layers to understand the contextual relationships, the semantic relationships, the relational entities one to each other. Those layers are called transformers, GPT, generative pre-trained transformers, and that's helpful to use for generating what comes next. GPT is a class of embedding models that have autoregressive prediction, which means that it can guess what may be the next thing in the data set, which is fantastic for all of our code completion tools. It's fantastic for when you want to help to produce the next paragraph in a paper. That's where that comes from. That's the embedding model process. It's not magic. It's actually a very simple kind of step-by-step process. So, and there's not just a few of them. There's a great resource, it's a funny kind of name, called Hugging Face. And Hugging Face contains information on all the open source models, including embedding models, which are a subset of models, as we mentioned. And there's not just 100 of them, not just 1,000 of them. There's some nearly 8,000 embedding models produced by universities, open source developers, companies, governments, all around the world. And they're all a little different one from each other, all a little nuanced one from each other. So there's thousands. We just covered GPT as one example, but there are so many more of these embedding models. So once you have taken your data and you've turned it into a vector embedding, and the user comes to your dApp and they want to search, they go to the search bar, that search gets turned also into a vector embedding. And now what happens for a similarity search, their query as a vector embedding gets searched against your data set, which is a vector embedding, to find the closest relationship, right? That's how that happens. It's called nearest neighbor search or similarity search. So for example, let's say you have a bit of a heterogeneous data in your data set. NFT metadata, recent transactions, ERC20 stuff, DAO proposals, all kinds of things. And the user comes to your dApp and they search on the search bar for something. That search gets vectorized, and then that search then finds its way to the closest part of your data that represents what they're searching for conceptually, semantically, etc. And then it goes even further into the subset of that data and returns only the most relevant results. It's pretty cool, and it basically creates a more intuitive, more natural feeling experience for your users. How does that all work, though? How does it find itself in what we call vector space? Now, I promise not to talk about too much math. Math is not my specialty either, but you may remember from middle school things like Euclidean math. Does that sound familiar? Or cosine? Right. Those are used in real life to help determine the closeness. One of the more simple ones, which also, interestingly enough, is one of the most commonly used ones, is called dot product similarity, which basically measures the sum of the two corresponding elements in the vectors. Higher sums are more similar, lower sums are less similar. That's often used for content recommendations like, you watch the British baking show, you may like the Australian barbecue show. That's happening with vector search using dot product similarity. So that's how closeness happens. At this point, my friends, you are pretty familiar with the basics of what vector search is, what a vector is, what a vector embedding is. You're pretty good. You got a good basis for it. And what's really important, what I really want you to understand, and if you don't understand this yet, you probably will by the end of this conference, by the end of, I don't know, the end of today, is that all of the AI-generated content, AI search, AI content recommendations, what you see, how you see it, what the data looks like, that's all being shaped by AI systems. And that's not going away. That's only getting more pervasive, more prevalent. We're not going backwards, we're only going forwards. So those who control the models, the embedding models, those who control the data, the compute on the networks, those folks, without overstating it, are going to basically control the world. Which maybe this might sound a little audacious, but therefore we really must find a way to decentralize at least part of the process. Because this has huge ramifications, huge implications for not any one area, for all areas of our life, of our society, of our information retrieval, of the ways we think about things. So much is how the data is shaped and the data is presented to us. So we really have to take a part in trying to find a way to decentralize that process. Which brings us to vector search in a blockchain. Now, vector search in blockchain is already being used in many ways. You may not be familiar with all of it, but it's being used in a lot of ways to do some of the things you see in Web 2 as well, provide more semantic search for metadata, give a more friendly user experience on your dApps, and also for advanced analytics and really fast and really efficient detection of fraud on our chains. That's already happening in many ways, but there's so much more that it can be done as well. So when we talk about vector search in blockchain, how do we train our models? Training the AI models is integral because that's where it all starts. That's basically, when you get to the vector search element, when you're searching, you're already at like step 2 or 3, 4, and 5. Training the model, that is step 0. That's ground zero. So training the models, instead of in a centralized paradigm, there's already been for years research and implementation of a more decentralized way of training. It's called federated learning. You may have heard of it before, maybe you haven't, federated or distributed learning. But there's a traditional model of federated learning, which presents some problems in our context. Primarily, it has a central aggregation node that coordinates the whole process. You hear the word central aggregation, and your brain is probably already spinning with all the issues that's present in that. Just to name a couple of them, you have a single point of failure. That's not good on a chain. That's definitely not good in training AI models. You have a central point of failure, which allows for the introduction of bad actors. And remember, AI models, embedding models, are not intelligent. They do what they're trained to do. So if you introduce malicious training, or you do things that are nefarious at the training stage, you are shaping the way users will interact with data and information going forward. So there's a lot of importance to wanting to prevent bad actors. And of course, another issue is just an issue that's prevalent all over Web 2, which is the lack of incentives for people volunteering their compute. Why should I make my computer, my machine, part of the training process as a node? What do I get out of it? You may tell me I get the self-satisfaction of being part of something. That's wonderful, that feels great. But I can't buy a cup of coffee with self-satisfaction. I can't pay my rent with self-satisfaction. I can't support my family with self-satisfaction. It's wonderful, kudos, but there's no incentive model there. As opposed to a more Web3 context where you decentralize the centralized aggregator, you spread it out, the responsibility amongst many nodes, you introduce smart contracts to regulate the behavior of the node operators, and you introduce incentive mechanisms into the entire process. The classic model looks very similar to this, and if you're curious and want to read about it, recommend that research paper. You can scan the QR code and really dive into it. Basically, you have a central node that sends out the global data. Each of the local nodes trains locally on their machine, then they send back that up to the central node, which aggregates all the training and then produces sort of a aggregated version of a training of a new AI model. That's the centralized, classic, federated machine learning model. Another alternative, and this is only one example, there are many examples, comes from this white paper from 0G, which you can see as well if you want to scan that QR code. The altitude here is just like wreaking havoc on my voice. You can scan that QR code and you can see that model. And what's really interesting there is you have a multi-node orchestration process. So instead of a centralized node actor, an aggregator actor, I should say, you have multiple nodes acting as the centralized aggregator, spreading it out, reducing the attack vector possibility, and making it harder to really tamper and interfere with the process. Okay, my friends, wherever you're watching this, wherever you are now experts on this topic. Okay, not really experts, but you're familiar with the topic. Let's actually talk about how this might be used in a Web3 context for the next few minutes. First of all, fraud detection. It is already clear and evident if you can use vector search to see what's similar, you can use vector search to see what is dissimilar. You can find anomalies in data patterns. And as you could probably guess, that's an excellent way to detect fraud. And Web3 is not the only one using it. In the Web2 context, there's a company called Revolut. Anyone familiar with Revolut? It's a British banking company. They're very popular in England and the UK. Or they have a love-hate relationship, I guess, like all banks. And they have a product called Sherlock. Part of it is open source, by the way, not the whole thing. But Sherlock detects within milliseconds fraud on a customer's account. And they do this in almost real time, millisecond time, for tens of millions of transactions all day. And basically, what that looks like is if you're a Revolut user, somebody uses your credit card for something, and you get a pop-up within seconds asking you to verify the transaction. If it's not your transaction, you can dispute it in seconds. That all happens with vector search. In the Web3 context, we can do something like this, using graph neural networks and vector search. Because remember, in a Web3 context, a lot of attacks happen through Sybil attacks and other forms of using multiple wallets, multiple, let's say, burner wallets to conduct a coordinated attack, which means it's not just enough to detect a single malicious actor. You need to detect the connections and understand where you see a behavioral pattern across wallet addresses, which means graph neural networks, constructing a graph of connections of transactions, is a fantastic way to do that. So you would feed in all the blockchain transactions, you would use a graph construction to understand where the illicit clusters are happening, feed that into an embedding model to detect the patterns, the anomalous patterns, and by the way, all of this can happen in millisecond time. Not sub-millisecond, we're not at that point yet, but millisecond time. That's pretty close to real time. That's pretty good for huge numbers of transactions, for millions of transactions a minute. This can happen at millisecond time. This is a great architectural model for implementing that in a Web3 context. Another great use case is discovering NFTs. This is a fun one for me, right? So let me just give you a quick example. I'm on a website, and I want to search for NFTs that are like anime stuff. So I search NFTs that look like anime. It's natural language, right? I get back, no results. Well, that's so sad. If I search for anime, what do I get back? Anime NFTs. What happened? That's an exact keyword match search. That's not helpful. That's not to shame that NFT marketplace. I'm sorry to do that. But it's not helpful. I want to search with human language. So using human language in my dApps, in my web portals, is just integral. It's really transformative. Can't stress that enough. Okay, so vector search unlocks a lot of personalized recommendations, content, intuitive user experiences. You can use it for DeFi apps for smarter yield and staking, Web3 social to find better discussions to participate in, cross-chain asset discovery, and don't forget creating better developer experience for builders when they're trying to figure out things in the docs, much more intuitive user experiences in your docs. But what about off-chain data? This is a big one, because a lot of our data doesn't live on-chain. like, for example, Oracle data. We are feeding in data from, weather reports and New York Stock Exchange and Reuters. You can use traditional vector search platforms to do the exact same thing with off-chain data, because blockchain data is resource constrained. Not everything has to live on-chain. And I will tell you, this may sound a bit audacious, but use Web 2 resources when it made sense. Because guess what, friends? We already are. We're using Notion, we're using Discord, we're using Telegram, we're using Vercel, we're using AWS. We might as well use Web 2 vector search platforms for off-chain data as well. We're already doing it, might as well do it now. And there's a lot of different options. There's Pinecone, Couchbase, Supabase, AWS, all of them offer this as options. Just to show you one example, with Couchbase, they have a free tier, free forever, no credit card required. You can actually bring vector search to offline edge, which means if you're on an airplane and you want to search on the NFT marketplace, you can do so offline mode using offline mobile vector search, which is pretty cool. And you can discover more about that by going to that QR code. So basically, just to sum it all up for you, the combination of off-chain data vectorized with on-chain data vectorized, when it's needed together in coordination, basically creates a more comprehensive, fuller user experience. And I want you never to forget, if you remember one thing from our time together, data is basically like garbage. It's only as useful as how you treat it. Data is like garbage. Now, if you're curious about this, I have a book coming out in a few months called Mastering Vector Search for Developers. It's basically like a 250-page tutorial. It'll take you through building a full-stack application with vector search. I will never email you except to tell you when the book is coming out with a coupon code. So you sign up for that mailing list, I promise you, the only email you will get from me is when the book is coming out. Thank you very much for your time. Have a great rest of the event.
Thank you so much, Ben. Super exciting. I know we're all looking forward to reading your book.
Thank you.
Next up, we have an exciting talk from the co-founders of the Monad Foundation, Eunice and Keone. They're going to talk about the Layer 1 innovations.